In this video, I'll be talking about real cells, or batteries, rather than ones that have zero internal resistance. Please read the success criteria of what I plan to cover in this video. Okay, so first let's talk about the idea of primary and secondary cells. And I keep using the word cells rather than the everyday word battery because it is more correct. A battery technically is a collection of cells. So if I use these four all together, then that would be a battery. One on its own, as you can see here, it says lithium cell. So a primary cell is one that cannot be recharged. So that's these examples here. You use them once, and when they're done, you need to throw them away. Be environmentally responsible and dispose of them properly. These ones tend to be zinc carbon or alkaline cells. A secondary cell, I've got one here. These ones might be, depending on what's written on them, a lead acid battery in your car are secondary cells. These ones can actually be recharged. So they're not use once and throw away, but rather you need something special to reverse the charge in them so that you can use them again. There are always warnings about putting these primary cells in a recharger. They are not designed to work like that. One other thing I want to point out about cells is this idea of a charge capacity. We see this a lot, especially on power banks, and let's just point out that power banks that you might use for your phone or other electronic devices are actually just a cell. The only difference is they're usually designed so that you can connect a USB to it, and you don't usually see a positive and negative side to it. But they are still a source of stored charge. Our charge capacity is the amount of charge that it actually has before it's drained and either has to be thrown out or recharged. We typically see them written as amp hours, which would be the total amount of charge. Here's our equation. Current times time, that's what those units are saying, amps times hours, which would give us charge. The only thing to remember about this is time really should be in seconds, and so 1 hour is 3,600 seconds. That's why 1 amp hour would be 3,600 coulombs. Okay, so let's also remind ourselves about the difference between EMF and a terminal voltage. The EMF, and I've got 3 different possible definitions here: the power supplied per unit current, or the work done per unit charge in moving a charge completely around the circuit. That's the one I usually use. Or the total energy per unit charge made available by the source. That's another one that's really good to use. So we've got the EMF here, and remember we've got an internal battery because these are real cells we're talking about, which means if this makes, for example, 9 volts, some of it is going to be used, that 9 volts, joules per charge, some of that's going to be used to move the charge carriers through the cell itself. That means out here in my circuit, I will not have the full 9 volts, but something slightly less. EMF then would be in a open circuit, so no currents flowing to the outside, but a terminal voltage would have a closed circuit, which means there's some current flowing through using some of the energy per charge, and then the rest comes out our circuit. As I said, this video is all about real cells, so we can't assume that little r equals 0. Now, don't panic. This is not a set of details that you need to know, but rather some things for completeness of this video, but also things to consider. I've taken this list of 5 things from circuitdigest.com. In terms of choosing which battery would be appropriate, they're suggesting energy density, which is something we talk about in topic 8 as well, the amount of energy per volume that we're actually getting. So in other words, is it a big bulky battery cell, or is it one that's more compact? The maximum rate of energy per mass or volume. So in other words, is it going to last a long time for the amount of volume I have? This is really important in things like laptops. The safety, in terms of the conditions it's in, some of these are not very good at very high temperatures because of the chemical reactions inside. The durability, how long is it going to be? For example, you don't want a smoke detector that has a battery that has a life cycle of only a couple of months. We want to have a long life cycle for those. And then obviously cost. So here's the list on this side about a few different types of batteries we have, in addition to the alkaline batteries that we were talking about before, like you would use on a flashlight, for example. The lithium batteries we tend to use in things like our iPhones, or the rechargeable batteries. We have other ones that would be inside, for example, your pacemaker, your hearing aids. They obviously have to have a different standard than what I'm going to put into my flashlight. And the lead acid battery, they are big and they're bulky, but they also can have a very large initial current that's really needed to start your car. So I said that real cells have an internal resistance, and we can't get around that. But not all batteries, not all cells have the same internal resistance. It's also not a constant value and typically increases as a battery gets older and it gets more and more used. They can also be affected by temperature. I remember on one trip that I had, we were in the snow and I had to keep putting my camera inside my jacket to keep it warm, because when it was out, it was getting so cold, the internal resistance of the batteries were so great, there was not enough current being produced for my camera to take a picture. Some of the first rechargeable cells also had what we called a memory. In other words, if you didn't deplete them all the way down to the lowest possible charge, then they developed like a memory, and they would actually get to that certain stage and would not give off their total charge before needing to be recharged. So speaking of recharging cells, let's think about what has to happen in order to recharge those batteries. We're going to have to put a current through our cell in the opposite direction, because we're going to have to go and reverse the chemical reaction that was inside it, that caused our current to happen in the first place. And this is why you can't just put any battery or any cell in a recharger, because they may not have a chemical reaction inside that was designed to be reversed. Now, once I do put it in my charger, I need to make sure that my charger has an EMF that's greater than the battery, so that I can cause the current to flow in the opposite direction. When I discharge that cell, we have said before that it has an internal resistance, and the other thing that's really important is the internal resistance isn't actually constant. But you can see from my graph here, the terminal voltage across my cell will start off and drop very quickly at the beginning, but then for most of its life it's actually going to be very constant until we get to the end. Let's go through a few different examples here. In a real circuit, the terminal potential difference is its closest to the EMF when. Let's start by writing our equation again. Or we expand that as the terminal voltage plus the current and the internal resistance. So what we're looking for is we're looking to reduce this factor right here. Let's talk about the last two. This is not always true with being charged and discharged. Only certain types are affected, so this is not a blanket statement we can say. If I look at B here, if I have a larger current, then this value of IR will be increased as well, and that means our EMF and our terminal voltage will be farther apart. Let's look here. The internal resistance is much smaller than the load resistance. Yes, that will reduce that last factor. Example 2. A rechargeable cell carries the markings 150 mAh. So what charge does this correspond to? Well, let's look at this value. So first of all, this says milliamp, so let's get rid of the milli. And this is for an hour, but in order for charge, we need to have that in seconds, so 3,600. Now, I should be able to do this without a calculator because it's under my multiple choice questions. So this is divide by 1,000. Let's just do this, 150. And if I divide this by 1,000, I get 3.6. Now, without picking up my calculator, if I multiply 150 by 3, that gives me 450. Well, these values are so different that I'm pretty sure right there it must be 540. You can use your calculator and check if you want. outline with reference to charge carriers what's meant by the internal resistance of a cell. So first, what we mean by charge carriers would be either electrons or ions inside the cell. And where current flows, they have to move through the cell. Because we have a real cell, that means they're not perfect, and energy is going to be dissipated as this happens. This is going to cause a lower potential difference for the circuit to use. And this is what we're referring to as internal resistance. Okay, for part B, the variable resistor is set to 1.5 ohms. When the cell converts 7.2 millijoules of energy, 5.8 millicoulombs of charge moves completely around the circuit. It asks us to show the EMF of the cell is 1.25 volts. Well, let's remember that volt is work per charge, or energy per charge. So that's going to be 7.2 times 10 to the power negative 3 over 5.8 times 10 to the minus 3, and I'm going to get 1.41 volts, which is approximately 1.25 volts. Remember, when it has to show that question, you need to show your working, you need to show the number substituted as well as your answer to make sure you get the mark. Never just go from the equation to the answer, even if you know it's right, because then you're not showing it and you will not get the mark for the question. Now for part 2 of B. It says determine the internal resistance of the cell. Well, first let's find the current that's flowing through. We know that in the variable resistor we have 1.5 ohms, and we also have a potential difference of 0.55, so we can calculate the current there. Using Ohm's law, moving it around, V over R is going to be 0.55 over 1.5, and that will give us 0.367 amperes. Now let's use our equation. E equals I R plus R. I'm now going to expand that out. We can also say that's our terminal voltage plus the current times the internal resistance. If I rearrange this, R is going to be epsilon minus V over our current, putting in our values, and it's better to use the unrounded values because I'm not at the end of my question, and I will get 1.9 ohms. So the internal resistance of my cell would be 1.9 ohms. So one of the things that's really important about this section is its applications to real life, and that would be recharging a battery. So I have a question here about just that. I have a power supply, in this case it says DC, so direct current, and it has a value of 5 volts. I'm going to set it in my circuit. You see I've got a simple series circuit that has my power supply and my batteries. Notice they're put in the opposite direction, so I'm going to get my current to flow in the way that they did not deliver the current beforehand, so I'm going to reverse the chemical reaction inside, and I have a resistor here. First part says what is meant by EMF. Remember, the example I usually use is work done per unit charge in moving charge completely around the circuit. Or you can say energy per unit charge made available by the source. Part B. So it goes on to tell us the EMF of the power supply and the EMF of the battery act against each other in the circuit, and the EMF of the battery is 3.7 volts. Calculate the current in the circuit. And for this I'm going to use Kirchhoff's voltage law. Kirchhoff's voltage law says the total potential difference around a loop will equal 0. So first of all, I've got the potential difference, or EMF, from my power source. I've got my battery in there in the opposite direction, so I'm going to put that as a negative. And then I also have that the potential difference across my resistor is also going to reduce what's given by the power supply, so I'm going to put it in as negative. And that will be its resistance times the current. And all that's going to have to equal 0. Let's put in the values we know. This is going to be 5 minus 3.7 minus 5.2 times I, which is what we're looking for. 1.3 minus 5.2 times I equals 0, and I will then be 0.25 amps. It now says we can assume that the current in the circuit remains constant as it's being charged. So calculate the charge that will pass through the resistor in 1.5 hours. Well, our equation will be charge is going to be the current times time. Our charge was found to be 0.25, and 1.5 hours will be 1.5 times 3,600, which is turning the hours into seconds, and I get 1,350 coulombs. So please take a moment and read the success criteria one more time. I hope you can say yes to all of these points.